Okay. Okay, so let's continue. Okay, so last term, okay, the marginal likelihood, okay, also known as evidence. Okay, so this, okay, is the probability of observing the data averaged over all possible values of the parameters can take. Okay, because it is not conditioned on certain parameters anyway. Okay, so for most of the class, okay, we will not care about the marginal likelihood, as we will think of it as a simple normalization factor. Okay, because eventually this evidence or marginal likelihood is going to be used to make sure the result is going to be a distribution. In other words, the integral, okay, part is going to be 1. Okay, so that's why, okay, this marginal likelihood is considered as a normalizing factor. Okay, so we can do this because when analyzing the posterior distribution, so we only care about the relative value of the parameters, not their absolute value, because this value, p theta on condition of y, okay, this y is actually just like d, okay, is proportional to the py on condition of d times p of d. Okay, so even though, okay, they are not the same, we know they are not the same. Okay, this one and this one, they are differed by a p of d, right? Divided or p of y. Okay, I mean, because we use y for d in this formula. But remember, p of d or p of y is a fixed value here. Okay, it's a fixed value. So it doesn't, that's why we can say they are, they are proportional. This one is proportional to that one. Okay, because the denominator is a constant. Even though we don't know what that is, okay? And also, when you collect the data, I mean, sometimes the data comes in batches, right? So, do you consider the ordering of the data has impact to a result? I mean, the base rule gets us from a prior belief, p of theta, to a posterior belief, p of theta, on condition of d. So when we take into account some data, obviously, okay, but suppose we observe some more data, okay, so we denote that as d prime. So we can then update our belief again. So p of theta on condition of d to p of theta on condition of d prime and d. But the question is, does our final belief depend on whether we update with d first and d prime second, or update with d prime first and d second? So is the order of the data, okay, is it going to play any role in the inference? Okay, so this is hard to say. Okay, it depends. Okay, it depends on the model function that defines the likelihood. Okay, so in many models, the probability of data, okay, does not depend in any way on other data. So that's the joint probability of p d prime on condition of theta will be the same as p of d on condition of theta times p of d prime on condition of theta. Normally, it's like that. So in other words, the data probabilities are independent. If you have this, then the order doesn't matter. Okay, the order doesn't matter. But it is not always the case. If the likelihood function has no dependencies on data ordering, then the posterior should not have any dependence on data ordering. So we can formally prove this, okay, because P of theta on condition of d prime d, we can write it like this, okay, and without changing the denominator becomes like this, because as we said, we have this, right? P d prime on condition of theta equal to this one. So we can break the denominator of this into this one. And we can break the numerator of this into this too as well. And then, okay, we can, reorder, because it's multiplication anyway, right? So we can change the order and then put them back to be like this. So P of theta on condition of d prime d is the same of P of theta on condition of d prime. If you have this, the German probability of d prime on condition of theta equal to P of d on condition of theta times P of d prime on condition of theta. If that's the case, then the order doesn't matter, okay? But it's not always the case, okay? If you ask, like, do we have any, like example that the order matters? Okay, one quick example I can come up with is like, okay, yeah, well, for example, okay, if you put, I just put in some sugar in my coffee, like during the break, okay, if you use like a sugar cube, okay, and then you put the sugar cube into your the cup, okay, and the sugar dissolve, right? The sugar dissolve into the water, or well, coffee, whatever you say, okay. So the sugar, dissolve, okay. The rate of the sugar dissolve, okay, depends on the surface, how much surface it has in contact with the water, right? You see what I'm saying? Okay, because the sugar, okay, 那个溶解的速度跟表面积有关系嘛 ？Yeah, the how much area, okay, the sugar cube, okay, has contact with water, okay, somewhat like determine like how quickly the sugar dissolve into the water. So when it is a big cube, when it's a big cube, it has a larger surface, right? So when you first put your sugar cube into the coffee, okay, it dissolves quickly. Okay, but when it becomes smaller, if you do not stir it,如果你不搅它的话, if you do not stir it, just put it there, okay, the smaller sugar cube dissolve slower, right? Because it doesn't have that much surface to get in touch with water, right? Okay, so basically, okay, so if you say like, okay, we put in a sugar and then, okay, let's measure like the sweetness, okay, the change of the sweetness of the water, okay, the first 10 seconds and the next 10 seconds, okay, this is dependent, right? This experiment is dependent, so the order matters. Okay, in some experiments, like the order matters. Okay, because it's this sampling. Okay, I mean when you do the experiment, I mean at this moment, okay, the sample you get here, it's something has changed. Okay, the cube, the rate of the cube dissolving, okay, obviously change. Okay, so well, I mean, it is not the order, okay, matters in this case. I mean, it's no longer independent. Yeah, I wanted to use like another example, but I kind of feel like it's not a good one to give, because like last weekend, I mean, my friend, we were drinking like a red wine and discussing like the most famous like news recently, like in Hong Kong, 那个女生被分尸，然后那个 okay, so we were, I mean, of course we are jokingly, okay, discuss like what is the best way to kill somebody like without being caught, So like we talk about like so our conclusion is like there's a case about more than 20 years ago, probably before you guys were born, okay, which was happened in Tsinghua University, inside the university. A female student killed his boyfriend. And then, okay, she was caught, okay, but I think her method is brilliant, okay, because she is into chemical engineering, chemical field. So what she did is like she used I don't know what the English term for that. 王水. Okay, she used 王水 to dissolve the corpse. She is almost successful, but the corpse takes time to dissolve. So she, before the job is completed, she was caught. Okay, so I kind of feel like if she really get the corpse dissolved, okay, that's what, I mean, it's like a link to the dissolvation. This thing. I mean, anyway, like it's difficult to be caught. Okay, I mean because the corpse corpse disappear, and then I mean because she is doing experiment, right? She get those like those material all the time, So it's difficult to say, oh, you may use this to dissolve corpse because she is into chemical department. She's a student in the chemical department. So it's so that thing is probably the most the best way to kill somebody without being caught. I don't know. Yeah, but anyway. Yeah, probably we shouldn't discuss this in this class, right? Okay. So anyway, okay. So so it's time to talk about a more concrete example. Even though this example is still discrete, okay. we still have to talk about discrete example because, as I said, like when it comes to integral, okay, because the continuous case always involve integral, and the integral is difficult to solve unless it's you are talking about conjugate prior. Conjugate prior. What is conjugate prior? We'll talk about that later. Okay, I mean you can say conjugate prior is a particular type of prior that can be that we can solve the integral to get a closed form easily. Okay, that's called conjugate prior. Okay, but for most of the case, I mean, the conjugate prior doesn't work anyway. Okay, unfortunately. So let's look at the discrete case first. Okay. So the coin flipping. Okay, this coin flipping problem or the beta binomial model. Okay, it's a beta binomial model because it's the distribution that we consider is a beta distribution, and the likelihood function is a binomial. Okay, binomial. Okay, so that's why we call it beta binomial model. So it's a classical problem in statistics, and goes like this. Okay, we toss a coin a number of times, and record how many heads and the tails we get. Okay, based on this data,